5.5 is the substitution rule. The substitution rule says if u equals g of x is a differentiable function whose range is an interval I and f is continuous in I, then the integral f of g of x times g prime of x is equal to the integral of f of u du. So as it stands, with everything that's written in black, it doesn't seem like this rule really helps us evaluate an integral. But the idea here is that if this little f of u in terms, this integral now has turned into something that's in terms of u and no longer x, so it's like a substitution, and you know the antiderivative of that little f, then you can take the step that's in blue and write down that antiderivative in terms of u, and then you go back to your in terms of x with your u equals g of x. So it's like a change of variables type of thing, but when you do this, you're also kind of changing the scale. So it's not just simply letting u equal g of x, we have this byproduct where we have g prime of x dx, or this g prime of x is in here, and that's equal to du. So one way to think of getting that relationship is if u equals g of x and you write the derivative of that in terms of our Newton notation on the right and the Leibniz notation on the left, then we have du over dx is equal to g prime of x. So writing this as a differential by multiplying both sides by dx, we get du is equal to g prime of x dx. So when we change the scale of our integral, we have to also take into account the rate of g. So that's what it is, and we'll see how to use it, and I'm going to tell you some more things about it after this example. So right now we're just going to use it. The integral of 2x times the quantity x squared plus 1 to the fourth power. So far we've had some pretty easy integrals where we just look at what's inside here and we're able to say, hey, I know the antiderivative of that, and that's the answer. But here notice we got a little kind of a lot going on here. We have a composite function, and then we got an x on the outside too. So this one could be handled in theory by expanding x squared plus 1 times itself 3 more times and then FOILing all that out. But that's a lot of work, and you can imagine if this power is even higher, then that wouldn't be practical at all. And then the idea is then we distribute the 2x. So in theory you could do that, but it's not real practical. And it turns out the substitution rule can be used for this. So let's start identifying the parts. First of all, you should identify the composite function. So sometimes the composite function is not obvious, but in this case it is. What we got here is x squared plus 1, that function to the fourth power. So it's a composite function where your u would be equal to x squared plus 1. So this would be the u to the fourth part, or up here this would be our f of u. So I'm just going to write over here that u, or g of x, is x squared plus 1. That's what's implied there. And so when we're looking at the left-hand side, we're trying to relate all this stuff here so that we can move to the right-hand side, the integral f of u du. So looking here, we have our f of u identified. What about the du part, or what about the g prime of x dx? So what you need to do next is, with your choice of, to make sure this works, of g of x or u, x squared plus 1, you take the derivative of that, and I'm going to do it in the Leibniz notation here. Du over dx then would be just 2x, and then what you do is you write this as a differential for du, 2x dx, and then you see this thing on the right, is that what I have for the rest of my stuff? Because that's what du is equal to. Or is that g prime of x dx? So notice that we have 2x, and we have dx here. So in fact, that is what we have, which means this thing is like it's perfectly made for the substitution rule. And I can go ahead and use it. So you don't have to write this in ever, but I'm just kind of making this clear here that in this step I'm using the substitution rule with my u is equal to x squared plus 1, that now what I have is the integral of u to the 4th du. Now look at how simple that looks. And then the next question you ask, well, first of all, it has to be entirely in terms of u. You can't have any x's and u's combination in here. In order to evaluate this integral correctly, it has to be entirely in terms of u. So that's what we have, and then the secondary thing is, hey, do I know how to take that integral with respect to u? And it's a real simple antiderivative for u to the 4th. It's simply 1/5 u to the 5th. And so you do it. We just took the integral there, and then you should back substitute your g of x was the x squared plus 1, or I should say the u, and we're done. So that's using the substitution rule. So a couple of things here. We learned with the fundamental theorem of calculus part 1 that derivatives and integrals undo each other. So kind of a nice little check here would be to take the derivative of that and see if you get the inside of the integral. So I'm going to take the derivative of this and see what I get. So notice we're going to use the chain rule here, and we got a constant multiple of 1/5. So that's the derivative of the outer function evaluated the inner function, constant multiple rule, and then derivative of the inside function is 2x. So notice these are going away, and we get exactly what we started with on the inside of our integral, which we'll call little f. Let me see if that notation conflicts with this. Oh yes, it does, of course. So that's what we were calling little f of x before, so I'll just call it inside of the integral. So maybe you would be able to do this without the rule by noticing, hey, this is kind of like the answer to a chain rule problem. And that's kind of what the substitution rule is doing. It's sort of undoing the chain rule. So if you notice that without using the substitution property, that would be okay. But it turns out the substitution rule can be used in some contexts where it's not just undoing the chain rule actually, and it's more powerful than that. So you better try to understand it at the simple level by using it, even if you can kind of skirt around not using it, just so you get a good handle on it and you can use it later. So some things to notice from this. Integration substitution rule is analogous rule to differentiation's chain rule. So it's sort of like undoing the chain rule. Turns out it can be more powerful than that, like I said, but at a basic level this is what it's doing. And notice in general that differentiation is easier to its counterpart of integration, meaning that, you know, the answer to the chain rule, noticing that, and then using some rule to undo it, and kind of going through this process that we just did, is more difficult than just going forward and using the chain rule. Having something simple like what we ended up for an answer and just taking the derivative of that. It's straightforward and you do it. This is more tricky, and that's unfortunately the case in general with integrals. So I have some steps here because it's not always as simple, and we're going to start out easy, but you'll see how this can be used in a little bit different situations than just the straightforward undoing the chain rule. So the first thing we did is we identified the u, which is our g of x, the inner part of the composite function. Sometimes it's not exactly that, but again, at a starting out, this is what you do. Then you find the du by just taking the derivative of the g of x it's du over dx in Leibniz notation, so if you want to do it that way, and then you pull over the dx, that's how you find du. Now, you have to compare that to your actual integral that you have and see if it's there. And that's getting into step 2. So your f of g of x, or your f of u, is going to be handled with that, but then you're looking for comparing that du with the rest of the integral, so it's automatically going to be dx and then the other junk. The one we did an example on was pretty straightforward because g prime of x was just 2x, and it seems like we're making like a big deal out of this when it was really straightforward. It was just 2x dx, and you let that equal du when we do this comparison. Sometimes it differs by a constant, and then you have to do a little bit of algebra to this du equals g prime of x dx equation, and you just pull over the constant and do what you need to do. So I'll do an example at the end of this recording that requires you to do that. Next, make the u substitution. So this is what the substitution rule is basically telling you to do. And then do the integral. Substitute back in terms of x. So use your u of g of x to do that. It's pretty simple. And then that's your answer. You do not have to do a check, but that's kind of a nice handy thing when you're not sure. Okay, so let's do another example. We have the integral of 3x squared times the root of x cubed plus 1. Alright, first thing is, unless you're being real crafty and thinking about undoing the chain rule and stuff like that, as far as elementary integral rules go, we do not have one that says 3x squared times the root of x cubed plus 1. That's kind of a complicated thing. Once you start getting good at this, you'll be like, oh, I see a composite function. The inside of the composite function, its derivative or something kind of like that is on the outside. That means you can use substitution. So there's going to be other choices along the road here, so we'll start thinking about that a little bit. So composite function, that's kind of something that is obvious. And this would be the root of u if we were trying to identify the inner function, which means u is equal to x cubed plus 1. So the next thing is find the derivative of u. It's 3x squared. Rewrite that as a differential du, 3x squared dx. Alright, now, is that exactly what we have for the rest of the junk? So that we can let dx and the other stuff in here be equal to du? Well, this is another kind of easy one here, where that's exactly what we have. Du is 3x squared times dx. The root x cubed plus 1 is taken care of by the f of u part, or square root of u specifically. So the next step, using substitution rule, is to rewrite this in terms of u. And it simply is root u du, which seems kind of nuts. But that's what it is. So now, is that integral easy? Well, again, first of all, is this all in terms of u? Yes. We did that change of variables successfully in this integral, and it's u to the 1/2 du, which is a piece of cake to take the integral of. So we add 1, we get 3/2, so it's going to be multiplication by 2/3, u to the 3/2, plus c, back substitute, so it's in terms of x, and you are done. X cubed plus 1, throw that back in there, and you're done. Oops. Alright, so we're done with that one. as well just do the check really quick since I have room here. So the idea here is we undid the chain rule, take the derivative of that, two-thirds times 3/2, use the chain rule, gotta multiply, whoops, 1/2 times 3x squared. Those go away. And we have exactly the inside of the integral. One more and we're done with the recording. So we have the integral of 2x minus 1, the root of that. Alrighty, now it may be tempting to do some illegal algebra here and try to break it up into the root of each term, but you can't do that. That's not allowed with algebra. It's not actually correct. So then what we got here is a composite function. You know, if we were taking the derivative of this thing, we use the chain rule. It's always kind of like a little hint that you can't just do the integral directly. Alright, so what we're looking at is substitution rule. Helps with the composite functions. So what we'd have here is integral of u. So our u is 2x minus 1. Derivative of that is 2. Right as the differential du by multiplying both sides by dx, 2dx. So now we want to compare this 2dx with the rest over here. Well, all we got is just dx. So dx versus 2dx are not the same. Whoops, didn't mean to erase all that. So here's where that step where you do algebra to this du equals 2dx, and if it just differs by this constant, you can actually fix this to work by just going ahead and multiplying by half or dividing by 2, and notice that we're solving for dx, that you can put in 1/2 du, and that would be totally fine to find the integral that results. It just differs by a constant because we have like a constant multiple rule for both integrals and derivatives. So doing it, the substitution here is 1/2 du for dx. Sorry, that's kind of messy. So what we have is integral u equals 1/2 du. So it wasn't quite exactly g prime dx, but because it only differed by a constant, we could do a bit of algebra to our du thing that we found using our choice of u, and so this was the problem we could handle after all. I can take the 1/2 out, so the constant's not an issue here, and I'm looking at the integral of u to the 1/2. Everything's in terms of u, so we add 1, get 3/2. So we're going to come out and have 2/3 out here, u to the 3/2 plus c. Just finish that up. 1/3, u to the 3/2. Oh wait, just kidding, I would plug in my u. 2x minus 1 to the 3/2 plus c. So that is the result, and we might as well check because we're on our last one for the recording. So what I'll do when we're back in class is we'll review this a bit, but then we'll go over the ones that are a little bit more tricky. Not going to do a whole lot of trickiness on the final exam, but for those of you that are taking Calc 2, the more you can learn about the substitution rule, the better. It is sort of like the chain rule when you take derivatives. It's kind of all over the place. You use it a lot, so it's a good thing to get down pat. So I'm taking the derivative of this thing, use the chain rule, and notice we have all sorts of cancellation stuff that goes on. And we have exactly our inside function. Of our integral. And that's it. We'll handle it again in class. Another thing we'll do is we'll talk about how to handle the substitution rule with numbers in here, which would be a definite integral. So we'll handle that in the next section, next time we look at this in class.